I welcome you to our machine learning class, and today we are at support vector machine part 2. So in our last class what we have seen is that what is the concept of maximum margin classifier, which is a linear classifier and which has a hard restriction of all the points being on right side of the decision boundary as well as the margin. And we see that how support vector classifier makes it more robust by adding the concept of slack variable and a slack budget. But still, one of the problem is non-linearity. So we'll look at kernel trick to overcome that. We will look at an outline of support vector regression, and finally we'll look at some of the advantages and disadvantages of support vector machine. So as we said that, if it was linearly separable, then maximum margin classifier and support vector classifier can work. But let's take this simple example. Okay, so this is in 1D. So this is one class, these green triangles and these blue squares are another class. So the task is I will have to put a point on this line such that on one side there are the blue squares and another side there are the green triangles. Okay, so if you think, you will see that it is not possible to have such a point. So what can be done? So what can be done is that we can take it at a higher dimension. Rather than looking at x, we can look at x1 square. So here are now 5 plus 4 points, total 9 points. So in x1 square dimension also I will have this 9 points. Okay, so now you see what is happening. Okay, so you have different values now. So this shows 16 and this is so at one dimension we have plotted x1 and another dimension we have plotted x1 square. So once we have done that, see what is happening. I can have a simple linear boundary and can classify them. So you see I have no additional feature, but I have just introduced one feature which is the square of x1. Okay, so it has taken it to a 2D and we can now again linearly classify them. So one of the ways to use it is that in the plane where it is non-linear, I add non-linear features so that in the enlarged feature space, the decision boundary is still linear. Okay, so this is one of the approach by which we can operate. Okay, so here there is change in finding the distance. Okay, so now higher order features are coming into place. All right. Okay, so that is how the problem formulation is little bit changing. So the first step is called as adding polynomial features. So why it is called polynomial kernel or what is kernel will come in a while. So basically we can add polynomial features just as we saw. Now you can understand that we can add many polynomial features. We can go on adding higher degree terms, interaction terms, but how far we'll go? That will be a huge number of features. Okay, and computations of that would be very unmanageable. Okay, so there comes something called as a kernel trick. Okay, so if you use kernel trick, what happens is that essentially what you did in the last class was that you have a feature x1, you converted that feature into another feature which is or another observation which is combination of two x1 comma x1 square, right? Okay, and then probably I have found distance between x1 comma x1 square and x2 comma x2 square. Not found distance but tried to find maybe similarity between them. Okay, so that's how we would have done, and we saw that this became a linearly separable class. But if you use this kernel trick, what happens is you don't take this, you don't need to convert each of these 9 points to this new plane and then calculate distance. Rather than that, if you apply this square on the distance itself, okay, so on the distance itself, then you get the new distance or new similarity between the observations. Okay, so this is one of the very important properties of the kernel, which is kind of magical, or why it is called as kernel trick. Okay, now let's look at the use of kernels. Okay, so the first type of kernel or most simple type of kernel is called as polynomial kernel. In fact, some people will go ahead and call this support vector classifier is with a linear kernel. Okay. Now, when you are having a polynomial kernel, this d actually gives the degree of the terms that you can add. So the example that we saw had degree 2. Similarly, if you had something of x1 cube, that will be degree 3. Okay, and so on and so forth. C is something we have already seen in last class, which is the slack budget, and R is a ratio which tells you the importance of higher degree terms with lower degree terms. Okay, so as you increase this d equal to 10 and r equal to 100, you see that your decision boundary becomes more curvy or more sharper. Okay, so this is how you can use these parameters. Now let's try to formalize the concept of kernel more. Okay, so how do we calculate similarity between 2 points, which are nothing but similarity between 2 vectors? So one of the ways of doing that is called as cosine similarity. Okay, so cosine similarity is nothing but the inner product or the dot product of the vector. Okay, only thing is that if it is a dot product, then it needs to be normalized. So what do you mean by normalized? When a vector's magnitude or norm is 1, then the vector is normalized. So we have taken a vector, for example, as 1, 2 and two other vectors minus 1, minus 2 and 2, 4. And then we have calculated the similarity between itself after we have normalized the vector. We have calculated the similarity of this vector with itself and these two in this column. So as you can see, the similarity of itself is 1. So basically this value ranges from minus 1 to plus 1. Okay, so it cannot be more similar than itself. Alright, so that's why similarity is 1. And minus 1, minus 2 is actually the reflection of this point on the other side, right? Other side of the axis. So that's why similarity is minus 1. It cannot be more dissimilar than that. Very interestingly, if you have something like 2, 4, okay, so the ratio is same, right? 1 is to 2 and 2 is to 4, the ratio is same. You will see that the similarity is 1, because when you take a vector, what happens is you connect the point 0, 0, okay, the 0 vector with 1, 1, right? So naturally you can 1, 2. So naturally you can understand that wherever you have 1, 2, same point or same vector, if you extend, you will have 2, 4. So this similarity measure, that's why is scale independent. Okay, all right. So now, in order to evaluate function fx, so what is function fx? So fx is a function which will take the test observation as an input and will give the output that what is the predicted class. Okay, so maybe we can represent something like this. So xi is the inner product. So xi is actually all the training observation. X is the unknown observation which you want to classify. So for each of the observations you are finding the dot product, and then you are using a weightage like alpha I, okay, which let's assume that may be uniform at this point. And this function, okay, so similarity of this and the intercept will give you which class it belongs to, isn't it? Now the question is, so just think about it, that for support vector machine, do you think all these endpoints matters? Didn't we talk about extreme observations which are support vectors? So essentially this converts to only the support vectors, okay, because for all others alpha I is 0. Okay, so this equation turns to only those i's which are part of the support vector. Okay, and if you compare with KNN, there also this fx was a function of the k nearest terms, right? So there maybe you will write I, which is a member of sk, okay, and then it is still a function of uh, the distance or similarity of those points. Okay, so KNN also can be represented in some of this form. Okay, now let us look at how this can be taken into a higher dimension. So if I want to find if I want to find distance between these points in a higher dimension, so one thing, as I said, can be done is we take this, okay, we take this at a higher dimension, take this at a higher dimension, and maybe find the inner product between them, okay. But it turns out that using the kernel trick, we don't need to do that. We don't need to change this. If we just change the distance function, okay, if we just take, the dth degree of this similarity function, it will give me the distance between these 2 points when we extend this to dth dimension, okay. And so this is the polynomial kernel that we saw. Another very famous kernel is called the radial kernel. So radial kernel is a exponential function of the point and the points that we are measuring with, and it also has a parameter of gamma. And now fx changes to a function of not only beta 0 and the dot product, but this new kernel. Okay, so this is how, what is happening is we are not changing anything on the observations, but the distance that we are calculating are not actually of the original feature space, but of some higher dimensional space, which can be polynomial, which can be radial. Okay. So, if you look at such a problem, you see that this purple class is basically surrounded by this blue class. And if you use our normal way of even polynomial fitting, so it is very, very difficult using a polynomial function and polynomial kernel and finding it out. Forget about your maximal margin classifier, forget about your support vector classifier, even a support vector machine with a polynomial kernel will not be able to fit it. However, if we use a radial basis kernel, we will be able to draw a boundary of this shape, okay, which will solve my purpose. Okay, so that's why we use radial basis kernels. Okay. So also at this point of time, I would also like to tell you that these support vectors or the reference points are also called or can be called as landmarks. Okay, so these points can be called as a landmark. Now so one way what we did in the last class was we changed this to higher dimension. So we introduced another feature x1 square by which you could separate it out. So here we are taking another approach. So we are introducing two new features, x2 and x3, which are not directly any polynomial of x. Okay, so what we are doing is, how we are doing it, we are taking 2 points. Okay, so we are taking 2 points over here, which is -2 and -1, which are marked. Okay, so these are two landmarks. So what I'm now going to do is I am going to find the distance of this point x with these two landmark points. But I am not going to calculate the linear distance, but a projected radial distance, which will be given by this formula. Okay. So basically, if we take lambda equal to 0.3 and we calculate, let's take a point x1 equal to 1. So, this x minus L for this point, it will be 1, and for this point, it will be 2. So, I calculate the values x2 and x3 like this. Okay. And so, these points are now two-dimensional. Okay. And they are represented by two new features. Okay. Which is x2 and x3. Now if you see, again what has happened is that when you have plotted using x2 and x3, these are very, very well separated. And this new point comes over here. Okay. So this new point comes over here. So this is also a very good example that how this problem, which was not linearly separable, using two new features where we have two landmarks, and we have calculated the new features as a distance with them, okay, we can have linearly separable classes. All right, now you can understand that you can have as many landmarks as possible, but that will make, of course, you can go into higher dimension, and the probability of getting more linearly separable classes will be higher, but at the same time you can understand that too many landmarks will also be unmanageable. Okay. So now one thing that is to be noticed is that support vector machine is by nature, by its principle, a binary classifier. Because so far whatever we have discussed, there is a supporting two supporting lines, one hyperplane and like that. So how do I extend this to multi-class? Can it not work on multi-class? So there are two strategies to extend this to multi-class. One is called as one versus one. So let's say there are three classes, okay, red, green and blue, okay, three classes. So what we do is now we build three C2 classifiers, okay, 3 into 2 by 2 or 3 classifiers. So we take all possible pairs. So we take red, green, green, blue and red blue, all the three. And for all three, what we do is we build SVM and then we take the test observation and we see what it says. Okay, so let's say the first one says it to be red, the next one says it to be green, the last one says it to be red. So if such happens, then we'll say that this belongs to red by majority voting. Okay, if there is a tie, then you can randomly assign to any class. This is one approach. Another approach is all versus one. So what we do is instead of this k into k minus 2 SVMs, we build only k SVMs for each class. So for each class, we make it a binary classification. So for red, we club green and blue and make it not red. Okay. So the two classes are red, not red. Similarly, we have blue, not blue, green, not green. And that's how we build the k SVMs. Okay. And how do I now find out that which class it will belong to? So what we'll do is for each one of these we have the decision boundary or the hyperplane. So we'll calculate the distance of the test observation from all these k hyperplanes. Okay, all these k hyperplanes like the way we know, right? So if x asterisk denote a test observation, so this will give you the distance of the corresponding hyperplane or corresponding decision boundary. So I calculate for each one of this and then assign to the class for which it is the farthest. Okay, so where we have more confidence. Now let's look at how this can be how there is an effect of a parameter called as gamma. So if you remember that radial basis function has a parameter called as gamma. Okay, so if the value of gamma is more, then you have only nearby points which are considered. All right, and if you have low gamma, then far away points are also considered. Okay, so this is an effect of gamma. This is also one of the important parameters. Now let's look at support vector regression. So here what we do is we change the objective function. So instead of trying to fit largest possible margin, we try to fit all the observations within the margin. Okay, with minimum variation. You remember in linear regression also what we wanted to do? We wanted to have minimum deviation. So here also it is like, so that is the maximum deviation we can have, and we will try to fit a line such that most of the lines are within that margin. Okay, so something of this sort. And there is a parameter called as epsilon. Okay, so anything within epsilon we don't find the error. Okay, that doesn't affect the model, but anything which goes beyond this, okay, so those are calculated, and that adds to the inefficiency of the model. Okay, so you can see that if epsilon is 1.5, then the decision boundary is wider, and epsilon is 0.5, then it is closer. Okay, now let us come to the concluding slide. So what is the advantage and disadvantage of SVM? So of course you know that SVM is very good when we have no idea of data, and it can work on various type, unstructured, semi-structured. The kernel trick is like magic, so that was really revolutionary. Okay, and we can solve any complex problem, any non-linear problem can be solved. Okay, so what are the disadvantages? All right, so choosing a good kernel function is not easy, and it can take long training time because the computation of the kernel is not easy. Okay, it is difficult to understand, right? So the third and fourth point is difficult to understand. You do not know how to make business interpret. So this is a black box model, and it has a lot of hyperparameters like cost, c, gamma, etc. So it is not easy to fine tune these parameters, right? So I think I could give you a good understanding of SVM. Now feel free to add your questions on the comment section. Happy learning.